Swayam Prabha. Digital India. Educated India.
In this lecture, we will be discussing the concept of convolution integral from the concept of convolution sum. Then we'll apply Laplace transform on this convolution integral and how we'll find the linear relationship between input and output. From this linear relationship, we'll find the transfer function concept, which will relate between input and output. Also, we'll be discussing why we have to assume zero initial condition for finding the transfer function. Because if you assume non-zero initial conditions, the principle of superposition cannot be applied. Then we'll conclude the lecture with some important properties of Laplace transform, which we'll be using in the later lectures. In this lecture, we'll be finding the transfer function for our system. Here we'll be using the concept of convolution integral and how we can find transfer function from this concept. If you remember, we have done this part already. If you remember, if you have LTI system, and if you apply some input xn and the output, we can write, or the impulse response we can write yn equal to summation k minus infinity to infinity xk hn minus k. So this is already have done how we came up with this expression. Now we'll be using this convolution sum. This is basically convolution sum. How can you use this concept to find the transfer function? Now, from this, also we can write y of t equal to, if you write in the series form, we can write k minus infinity u k h t minus k. This is also the same thing, basically same expression we are writing in, just we change the, instead of n, we change the time. Now, the summation of the above equation, this is equation number 1, above equation 1 is replaced by the following integral. So we can write y of t, also we can write in terms of integral. Instead of summation, we can write in integral form, minus infinity to infinity u of tau is t minus tau d tau. This expression also can write from this convolution sum. And let me define this equation number 2. Now, okay, this is actually called, this part is called convolution sum, and this is we call convolution integral, because it is in the summation form and this is in integral form, equation 2. Now we shall use this concept to find the convert in the Laplace domain. Now it is in time domain. Now if you want to find the transfer function from this approach is quite difficult. So now we'll be considering some indirect approach using the Laplace transform. And for any function y of t, for any function y of t, the Laplace transform we can write ys equal to minus infinity y of t e to the minus st and dt. So this is basically, we can write Laplace transform of y. Okay, the same thing. And applying the convolution theorem here, in place of yt, if you substitute equation 2, let me write equation number 3. If you substitute equation 2 in equation 3, is it in place of yt, we can write y is equal to minus infinity to infinity again minus infinity to infinity is tau u t minus tau d tau e to the minus st dt. So here, since we are talking about the LTI system, and it means the linear time invariant system. So for time invariant system, instead of this, we can write this expression. We just changing the time. So it is same expression, same value will come up. Does not change for if you shift the time. So that is possible. Now, if you change the integration order, if we exchange the order of integration, we can write y is integration minus infinity u t minus tau e to the minus st dt h tau d tau. This is also you can write. And let me write, this is equation number 4. This is equation number 5. Now, if you changing the variables of the inner integral by defining t minus tau equal to eta, we get the following. We have the following expression. Y of s equal to, I can write minus infinity u eta e to the power s into eta plus tau d eta h tau d tau. We can write. Just we are replacing the changing the inner integral, and we are replacing the time with this parameter eta. And we can further write from this expression minus infinity infinity u eta e to the minus s eta d eta and minus infinity infinity h tau e to the minus s tau and d tau. And from this we can write, this is basically us. This is the Laplace transform of ut. And from the second part, we can write hs. So from this, we can write us hs. This is very, very important equation from this expression. This is basically very, very important equation for finding the transfer function. So now let me define it. What is this? So here us, I should write Laplace transform of the input time function, and h is Laplace transform of impulse response. So this is very, we have to use when you are talking about what is the transfer function, we have to write this Laplace transform of the response. So now by this operation, the complicated convolution integral is replaced by a simple multiplication of the transforms. So now we need to interpret about this thing, what you have done here, how we can do more treatment, and how we can come up with a better understanding on a transfer function. Now we have a transfer function h of s, and we are applying some exponential input function u of t equal to the word st, and the output from this transfer function block you can write y of t in time domain h of s into st. So here basically s is a complex number, sigma 1 plus j omega. Again, this is the real value, this is the imaginary part. So now we'll prove it how we are getting this expression through the concept of convolution integral proof. So here y of t we can write minus infinity to infinity h of tau u t minus tau d tau, and from this we can write minus infinity to infinity h tau e to the power s t minus tau. From this concept we can write, in place of t minus tau you can write ut minus tau, you can write e to the power s t minus tau, and into d tau. Further we can write minus infinity to infinity h tau e to the power st e to the power minus s tau and d tau, or we can write minus infinity to infinity h tau s tau d tau e to the power st. So this is nothing but our h of s. So we can write h of s e to the power s t. So this is what you are getting from this part also. The same expression we are getting through this proof. We'll go through why the initial conditions, because initial conditions assumed to be zero, first of all. Since we'll be dealing with the linear system, and also in the next few lectures, we'll be dealing with the transfer functions, and it will be assumed that the initial conditions for finding the transfer function to be zero, assumed to be zero. So why we have to assume the initial conditions for finding the transfer function in the linear system assumed to be zero? Let's look at it, why you have to assume. So in the integral limits on the integral, it conveys that minus infinity to infinity, and which implying that h of t may have values at any time. So it can take any values from the minus infinity to infinity. So initial condition not required. But for causal system, if you see the causal system, h of t will be zero for t less than zero. So if I write in the h of t, basically if you write in the frequency domain, you'll have h of s, this is we know, minus infinity to infinity, h of tau e to the minus s tau and d tau. This is the function we have found it here, if you notice here. So now, so for the causal system, if we assume the causal system, then for t less than zero, the h of t should be zero. So now, based on this condition, we can write h of s. We can write 0 to infinity h of t, sorry, tau e to the minus s tau and d tau. And correspondingly, for causal system, y of t, the output, we can write 0 to infinity h of tau u t minus tau d tau. So that's why most of the system will be dealing in this in the classical controls or causal system. So that's why we'll be assuming the initial conditions to be zero. So let's look another way. Why? What is the relevance? Why you have to assume the initial conditions to be zero? So here, if we assume non-zero initial condition, the superposition principle cannot be applied or validated. And another condition, we are assuming that the system starts from equilibrium point. If you go back to the lectures, generally how the system got disturbed from the equilibrium point. So if they start from equilibrium point, noted that the equilibrium point for LTI system is always 0. So that's why we are in the transfer function methods, we'll be assuming the initial condition to be 0. So now I'd like to highlight some important properties of Laplace transform and how we can come up with the linearity or this differential or integral, how we can come up with the some standard Laplace transform of those functions, because we'll be using very repeatedly in our subsequent lectures some important properties of Laplace transform. Some important properties of Laplace transform. So first is we'll be talking linearity. Linearity. If A is a constant and Laplace transform of ft equal to fs, then Laplace transform of aft, we can write a into Laplace transform of ft, which is afs. Now we'll be taking another second part, translation in time. Translation in time. If Laplace transform of ft is a function which yields to be fs and a is a positive number, positive real number, such that if t minus a equal to 0 for 0t, then we can write Laplace transform of if t minus a, we can write e to the minus is fs. So these are the functions we'll be using in our subsequent lectures. And third, translation in Laplace domain. If Laplace transform function ft, fs, and a is a complex number, then we can write Laplace transform of e to the power at f of t, we can write fs minus a. Fourth, real differentiation. If Laplace transform of ft equal to fs and if dft by dt is Laplace transformable then we can write Laplace transform of df dt is fs minus f0 plus. So here a 0 plus indicates that here if small f, we can write f0 plus, we can write, it indicates actually value of ft in the limit t tends to 0, approaching from positive side. So this is the first derivative, first term derivative. If you take the kth derivative, so if you have a function for the function dkft dt k, if you want to take the Laplace transform of this function, we can write Laplace transform of dk ft dt k equal to sk fs minus sk minus 1 f0 plus sk minus 2 df naught dt minus dk minus 1 dt k minus 1 f0 plus. So this is how we can find the Laplace transform of a derivative differential function. Now we'll take an integral. How we can find the Laplace transform integral function? Real integration. If Laplace transform of function ft equal to fs and the indefinite integral f t dt is Laplace transformable, then we can write Laplace transform of integration ft dt, we can write fs by s plus 1 upon s minus f into 0 ft dt. But later we'll be assuming, since we'll be dealing with the positive values of t, so we will not consider the initial conditions. Later we'll be explaining how it is coming up. So here note that the integral term on the right hand side is 0 if ft equal to 0 for t less than 0. So if you have another example, infinite, this is very important, sixth number, initial value theorem. I'll find the Laplace transform of the initial value theorem in time domain. If Laplace transform of ft yields to be fs and df dt is transformable and limit t tends to infinity as fs exists, then we can write f0 plus limit s tends to infinity as fs. This is we'll be using very frequently while we'll be talking on control design on steady state behavior of the system. If the flight is going to equilibrium point, and how we can find whether they're exactly going to equilibrium point or not, or the desired values or not, this thing we'll be using for finding the steady state error in the system. And 7, the final value theorem. If f of t and df dt is Laplace transformable and limit t tends to infinity, f of t equal to f infinity exists, then we can write f of infinity limit s tends to 0 is fs. So this is we'll be using for the steady state behavior of the system, how we can find the error once the system goes to, suppose this is my response, this is the desired response. I want to fly my aircraft. Now that is if the system goes like this, and if there are some error at the steady state, to find this amount of error, how we can find this error, we will be using this final value theorem. So let's stop it here. We'll be continuing from the next lecture. In the next lecture, we'll be talking how we can find the transfer function of a system, and also why you have to assume the initial condition to be 0 in the transfer function. And also we'll be coming up the concept of pole 0 in the system, in the transfer function, how you can come up with the poles and zeros of the system. So thank you very much. We'll continue for the next lecture.